Good morning, everyone. Okay, so welcome to our lecture. Okay, so for today, basically what we're going to be doing is going to be quite exciting. All right, especially the demo part. All right, so we're going to finish up the UART set of slides. Okay, and once we are done with that, we're going to look at this week's lab. Okay, so this week's lab there's two parts to it. The first part is, of course, to make sure that the basic UART functionality on the KL25Z is correctly configured. All right. The next part is where you're going to integrate the ESP32 and the app and everything. Okay. So this is the lab that you must do a demo for. Okay. Now the demo, you only need to complete it after you come back from the recess week. Okay, so you do not need to do any demo this week. Okay, this week you just start the work first. Okay, and next week is the recess week. Okay, so when you come back from the recess week, that Friday, then is when you need to do the demo of all of this stuff over here. Okay, and the main reason why this particular lab I want the demo to be done is to make sure that every team has the basic framework already in place. Okay, because once this framework is there, then you know that you already have a system where the user can send commands, okay, through Wi-Fi, okay, through the ESP32 and the KL25Z to control the robot. All right, and that also gives you the confidence to start integrating the other things that we have done, the PWM, the audio. So all this hardware stuff can actually start to be integrated already. Okay, once you start and you finish up this demo. Okay, because you have the confidence that you have the framework there. Okay, and as you complete all these low-level libraries, all right, and you put things together, then in the second half, when we go to the OS and understand how to create the OS architecture for the project, then it's a matter of coming up with your own strategy to design the architecture and putting all these libraries together with the architecture and getting the whole thing running. Okay, so it's getting more exciting. Okay, and of course there's also more work to be done. All right, but I think that if you manage the workload, okay, within the team, it will definitely be manageable. All right, I mean, to put things in perspective, this project, the same project that you're doing, was a two-person team a few semesters ago. Okay, so two people came together to do one complete system. Okay, then over the patches, I increased to 3 and now it's 4. Okay, so definitely it is manageable work. Okay, if you split up among the team, all right, different people handle different parts of the hardware or the software. Okay, definitely it can be done. Okay, so I think it's just something that needs to be worked out within the team. All right, so let me get started. Okay, and then we can continue. Okay, so last week we basically had a quick introduction of the UART module. Okay, so now what we're going to be doing is we're going to go more in depth into the overall details. Okay, and how we can sort of program it. Okay, so what we're going to be looking at is basically the overall software structure, all right, and of course the later part of the hardware configuration. So in terms of the software structure for UART, I think we already know that generally we can always use polling, okay, or we use interrupts. Okay, so it all depends on the nature of how frequently the data comes, and how you want to deal with the data, and whether you're busy with other things and so on. Okay, so you can use either approach, okay, depending on how you want to design the system. Okay, so in this example, all right, as you can see here, you can have interrupt. Okay, so this is just an example only, that where you have interrupt to handle the serial communication. Okay, and then from the interrupt service routines, you are able to translate the data to other parts of the program. Okay, in the Cortex M0 Plus, you only have a single IRQ handler. Okay, so in this example here, they're just giving a generalized example that you have one ISR for transmit and one ISR for receive. Okay, so some microcontrollers may have this functionality, all right, where you have separate interrupts service routine for different events. In the Cortex M0 Plus that we are having, you only have a single IRQ handler. Okay, so whether it's transmit, whether it's receive, whether it's an error condition, anything, everything comes within the same ISR. Okay, then what you need to do is you need to figure out what happened by checking the flags and then process it accordingly. Okay, so now what we're going to do is we're going to look at a concept of using queues to handle data. All right, now what usually happens? Okay, what usually happens when I cover this part of the lecture is many students immediately take this entire code base and dump it into their program and start to implement queues for their project, and then something doesn't quite gel and then things don't work. Okay, so the first thing, okay, is queues are of course an efficient way to manage data that is coming through some other channel, all right, and you want to manage it on when to read, when to update, and so on. Okay, but in our case, in our project, okay, we don't need queues. Okay, we don't need queues. Why we don't need queues? Because in our project, what is happening is you have a app, okay, that is going to send data. So eventually it comes to the, okay, so this is the app, and it eventually, okay, so from the ESP32 it goes to the KL25Z, okay, and then you control something, either the motor, the LED, or whatever. Okay, and in our project, the system is supposed to respond the moment this event occurs. That means the moment I send a data packet over, I am supposed to immediately decode it and process and carry out the correct action. Okay, so if I send a command to say move the motor, I expect the robot to respond by moving the motor immediately. Okay, it's not that I say that okay, move the motor about 2 minutes later. I'm not going to send a command like that. Okay, so whatever command I send, I expect the response to be immediate. Okay, so in our scenario, there is no need to buffer any data. So you don't need to create any buffer and then process the data slowly. No, you don't have time for that. The moment incoming packet is received, you straight away decode and you process it. Okay, there is no time to waste. Okay, so this circular queues, queues or circular buffers and so on, they are very useful in cases where you are sending data or you're expecting to receive data from some location. Okay, but you don't need to immediately process it, all right, or you can take your time to process it. Okay, but the processing may take a while, so you need to be able to buffer the data as it comes. Okay, so that is where these kind of queues are very useful. Okay, so for our project, you don't need to implement queues. You just directly deal with the data as and when it arrives. Okay, so let me say that first, because I know many students immediately go and say, I want to implement queue, but you don't need to. Okay, because if you implement a queue, is really a waste of your resource. Okay, because the moment the data comes, you have to dequeue it anyway. You don't have time to buffer anything and then keep it and slowly process it. No. Okay. So let's look at this concept of queues. All right. So in the concept of queues, basically what you have is you have a queue. All right, and the queue can either be empty, okay, can be full, okay, and what we're trying to do is we are trying to manage the queue such that whenever I need to read, I read from the head, which is the front of the queue. When I need to update, I write to the tail, which is the end of the queue. Okay, so that is the idea behind a queue. Okay, so let's see how we can implement this over here. Okay, so in this case, okay, firstly we define a structure. Okay, so we define a structure which is of type Q, so Qt, and I create two structure variables, txq and rxq. Again, the queue size, again, this is just a random number 32. That means I can have 32 elements inside my queue. All right. Now, inside, so first we declare this, define the structure and declare two variables, okay, RTSQ and RFQ. Now let's look at the code. All right. So the code is basically first you initialize. So when you initialize the queue, all right. So let's assume that the queue is here. All right. So the queue initially, I will point the head and the tail both are in the same place. So head and tail are both in the same place. All right. So initially it is empty, so the size is also 0. All right. And here what they've done is they have just cleared all the initial data to 0. So I make sure that all the initial data in the queue is 0. So there is no random value inside. Okay. And how do I know if the queue is empty? I know the queue is empty if the size is 0. Okay, how do I know if it's full? If the size, okay, is equal to the maximum size. Okay, this variable queue size is something that will increment as and when, or increment or decrement as and when you add or remove elements to the queue. Okay, but the maximum size is this queue size that you define. Okay, so these are the basic functions to initialize the queue, check whether it's empty, and check whether it's full. Now, the two important functions here, NQ and DQ. So when I say NQ, what will happen? All right, so let's look at an example. All right, so let's go to the same concept. So initially it's empty. So let's assume that the head is here and the tail is also here. All right. Now, and I pass in a data. I call NQ and I pass in a data, let's say 0xa. Okay, that I want to put into my queue. Okay, so whenever I add to the queue, okay, when I want to add, I will first check whether it is full. Okay, so if it's full, of course, I can't do anything. Okay, that means I return 0, is a failure. Okay, because the queue is full means I can't add any more elements to the queue. Now, if it is not full, then what do? I update it based on the current tail pointer. Okay, because you always add to the end, towards the end, and you read from the front. Okay, so if now I NQ the data, the tail is pointing to element 0. So this element 0, this element 1, and so on. Okay. So what I will do is the value that I pass in 0xa will come here. Okay, and then the tail will plus. That means the tail from here will now come here. Okay. Now the next step is Q tail percentage equals size. Okay, so this is to do what? This is to wrap around. Okay, why? If I keep adding until I reach the final, correct? Then when I increment by one more, I do not want to go beyond the space, correct? So I wrap around, so I'll come back here. Okay, so that is the wrap around to say that you have reached the end of the queue. All right, so once you hit that, of course, you will be able, you will not be able to add anymore. All right, and once I add a new element to the tail side, I also increment my size. Okay, I also increment my size. Okay, and then I return. Okay, so that is to NQ, that means add elements to the queue. Now, when I want to DQ, okay, when I want to DQ, I will read elements from the front of the queue, that means the head. Okay, so again, I must check whether it's empty. If it's empty, means there's nothing to DQ. Okay, so I will just return. But if there is not empty, that means there is some data. So what I can do is I will return based on wherever the head is pointing. So if the head is pointing here, then I DQ this data. Okay, so when I DQ this data, okay, when I DQ this data, what happens? Okay, I will now increment. Okay, I will first update the value to 0 and then I increment the head plus. So after I read the 0xa, that means this one is dequeued. Okay, I put in a 0. I put in a value of 0 inside. Okay, so again, this implementation is just example only. It doesn't mean that you have to do it. All right, but in this example, why we are just always making sure the default value is 0 is so that any non-zero value would mean that it is a data that was added by the software. Okay, so I replace that current data with a 0. Okay, then again I do this to wrap around. Why? Because if I reach the end, I go back to the beginning again. All right, so that is to do the wrap around, and finally I decrease my size. Okay, so if let's say I add one element and I remove one element, what happened? Then both my head and tail are still now pointing to the same location. All right, and if head and tail are both pointing to the same location, it basically means that the queue is empty. Correct, the queue is empty. So every time I add an element, the tail will move. When I remove an element, the head will move. All right, if they are both together, that means the queue is empty. Okay, and when I reach the end, I will go back to the beginning because I wrap around. Okay, so it's a very simple sort of way, okay, where we sort of structure where we use the array, okay, but we manage the data as and when it comes in. Okay, so how do I use the queue? Whenever I want to add something, I enqueue the data. When I want to extract something, I dequeue the data. Okay, so again, like I said, this is a very useful tool. Okay, if you expect or you're in a situation where you have a lot of incoming data, all right, but you need time to process the data, okay, and you're not in a rush to do it immediately, so you can sort of enqueue it in a circular buffer like this, all right, until some point of time where you have time to slowly dequeue everything and process it. Okay, so that is one way of implementing a structure to receive data. Okay, so how now when I receive the data, okay, I receive the data, how do I make sense of it? So how do I pass messages? Okay, so when I receive the data, okay, there are two ways in which you can send data. If you, those of you who have done our EPP2, I think majority have done it. Okay, if you look back at the code base that we gave you, okay, the serialize and all the stuff. Basically, what we do is we create an entire structure. All right, so we have a header, okay, then we have a data, okay, and the data itself has a certain number of bytes. All right, and then we have the CRC and all this stuff. Okay, so we created an entire structure for the data, okay, to be transmitted. Okay, so this of course consists of many bytes. Okay, which means that when I want to send one packet over, I need to send, okay, X number of bytes across, okay, the device, okay, across the channel, and only when the receiver receives this X number of bytes, then I can sort of re-engineer the structure, okay, and then look at the data that I have. Okay, so that is of course a good sort of framework if you have to deal with a lot of complex data that you need a lot of bytes of information. All right, in our case, all right, what we can do is actually we don't need to make it so complicated. We can simplify the whole thing and sort of use just one byte, okay, and decode it in terms of binary bits to decide what you should do. Okay, so for example, okay, when I send and receive, everything is in 1 byte. Okay, so what you can do is you can decide how you want to encode the bytes. All right, so for example, you can say 2 bits I set aside for motor control. Okay, or not specifically motor control, maybe I can set aside 2 bits for actual movement. Okay, is it forward, reverse, left, right, or whatever? Okay, or 3 bits, up to you. Okay, basically what you need to do is on your app, when I press a button, okay, let's say I have a button that says forward. Okay, when I press this button, okay, I need to be able to send some data packet over to the KL25Z. Okay, as long as the KL25Z interpret this incoming data, so let's say it's 0x03, okay, and I take this data and inside my code, I say that if 0x03, then it will be considered forward. Okay, of course, I'm just simplifying the whole thing. You may need to do some bit masking and so on to check for maybe only this particular bits and so on. All right, but the idea is that, okay, so you look at some specific bits to know what to do. Okay, now of course you will probably think that, but it's not just moving, correct? Your robot is supposed to do a lot of other stuff, correct? You need to control the LED, you need to control the audio, okay, and all this stuff. So how do I encode that all inside here? And the thing is, you don't need to, correct? You don't need to, because you can do that. You can do that here, okay, in the data packet that you transmit, or you can interpret it over here in the KL25Z, because the behavior of the audio or the behavior of the LED is tied very much to the movement. All right, so if I'm moving forward, certain things, moving backwards, certain things, and so on. All right, so inside the KL25Z also, I can choose to make the decision that if the movement is forward, what do I do? If the movement is reverse, what do I do? And so on. Okay, so there are different ways in which you can sort of plan it out. Okay, you can say that I decide everything in the app and just send everything over in the byte. So maybe 2 bits for movement, 2 bits for LED, 2 bits for audio, and things like that. Okay, so that's up to you. Okay, you can say that the app will send a particular data packet and I will just extract out and use that to control all the subsystem in the KL25Z. Okay, or I can say that I just send the movement that I'm supposed to complete, all right, and then the rest of the decision can be made within the KL25Z. All right, so there are different ways you can go about sort of planning this sort of message passing approach. Okay, so you will probably test out some certain things, okay, and then you will see what works for you or what is the method you prefer. Okay, but as long as the controller is able to decode the message correctly and perform the necessary action, then it's fine. Okay, so that is the general idea. So let's look at the KL25Z in particular. All right. So in the KL25Z, we have all these peripherals. Okay, so again, a few pins are UART, a few pins are SPI and I2C. All right, so again, most likely next batch, I might let go of UART and switch to I2C or SPI. Okay, either one. Okay, so yeah, I will let you all know as well. All right, once those material are ready. So if you're interested to explore that on your board, you can do that. Okay, so in terms of the clock gating, so the first thing is, of course, you need to set the clock gating bit. Okay, so that is inside SCGC4 register. So that is to switch on the particular UART module, okay, whether it's UART 0, 1, or 2. So you have 3 UARTs, okay, and you can decide which one to use. All right, but there is a slight limitation in the sense that UART 0 is already used in the debugger mode. Okay, so when you connect your USB cable, all right, to download your code, you're actually using UART 0 already. Okay, so UART 0 is not available, all right, because you are using that to download the code. Okay, UART 1 and UART 2 are the ones that are available. All right, so even though it has slightly lesser features, okay, but the basic serial functionality is there, okay, and that is all that we need. Okay, so this is basically the block diagram, okay, of how the UART transmitter looks like. Okay, I think most serial blocks have very similar concepts where you write data to a register and that register will get that information will go to a shift register. Okay, so when you transmit you are converting from sort of parallel data to serial data. So that is done by shifting the data, so bit by bit. Okay, so you shift out the data, all right, and of course, to shift out the data, you also need to determine the rate, the baud rate. Okay, so that you have some other clock generation configuration to be done. Okay, and of course, besides that, you may also want to generate parity. Okay, as we saw last week, to do some error detection. Okay, and of course, the last one is interrupts. Okay, so if I want any interrupt to be generated, okay, whenever I transmit the data, then I can enable the appropriate flags. Okay, so this is quite standard. So almost any microcontroller you take up, if you look at the configuration and the design of the UART module, you will see something similar. Okay, only thing is some may have a bit more features, some may have slightly lesser features, and so on. Okay, for the receiver is again similar. You have data coming in through a pin. Okay, and of course there will be some hardware circuitry to detect the logic and so on. Okay, but eventually once you get that data coming in, okay, you will be able to take that data and pass it into the shift register. Okay, of course the rate at which you sample the data is also determined by the baud rate. Okay, so transmitter and receiver both must have a same baud rate in order to make sure that the sampling is done correctly. Okay, and as you receive the data serially, you shift it into a register, and eventually you convert the serial to a parallel sort of format. Okay, when you read the entire register out. All right, and again, as before, if you want to have any interrupt, okay, you can configure those interrupt bits accordingly. Okay, now in terms of how do you deal with handling noise? All right, so whenever you transmit data across a channel, okay, within the board itself usually is quite safe. Okay, even though things can still go wrong, but it's still very, very safe. But once you bring data out, okay, that means from the microcontroller, you connect a wire out to some other board or some other component. Okay, there is a lot of noise that will interfere with the signal coming in. All right, so even though you transmit as okay 1 0, okay 1 0, you know 1, okay, and this could be 1 or 0, okay, something like this. Okay, the actual data that you get may actually be quite different, okay, depending on how much noise or interference is affecting that line. Okay, so to manage this better, okay, one of the things that the KL25Z does is it does what we call oversampling. Okay, so in oversampling, what we do is within that same pulse width duration, okay, I sample many times. Okay, and then I do some majority vote to decide what should be the value for this particular pulse that I get. Okay, and this again helps because generally when there is noise, in most cases you get noise spikes. Okay, sometimes so maybe you might get a spike over here. Okay, or in some cases, usually the beginning or the ending there is some sort of transition of the signal. Okay, so the majority vote, okay, helps to make the decision more accurate. Okay, to reduce the number of errors that we have. So for the UART1 and UART2 module that we are using, okay, we have a 16 times oversampling. So this is fixed. Okay, this is fixed. There is no change to this. Okay, so in terms of the baud rate generator, okay, what we need to do is we need to just implement it based on this formula over here. Okay, where the depending on whatever baud rate that we want, okay, we use this formula. Okay, so the module clock, okay, later I will show you which module clock to use. Okay, and the register that you want to update is this, the baud rate SBR register 12 to 0. Okay, and this multiply by 16. Why we need to do this is because of the 16 times overclocking, oversampling that we do at the receiver side. Okay, so we need to factor this in, okay, when we are deciding on the baud rate. Okay, so again, this formula will come back to this later, okay, when we have a look at the code. All right, so how do I configure the transmit and the receive? All right, so to transmit the data, okay, I can only transmit when the transmit buffer is empty. Okay, so where is the transmit buffer? So let me come back here. So this is the transmit buffer. So when the transmit buffer is empty, I can transmit. Okay, so I can write a new value into the UART register. And once I write a new data, it will come inside here and it will start to get shifted out. Okay, so when it starts to get shifted out, okay, so what I need to do is this. I just need to hold this particular flag, TDRE, transmit data register empty, okay, and check whether it's empty. If it's empty, then I can write to the UART register. Okay, when can I receive? I can only receive when I know that the receive data register flag is set. Okay, so when the receive data register flag, so where is that? Let me show you here. Okay, so that is over. Is it shown here? Okay, so the flag is not shown here, but basically once the data has been fully shifted in and I transmit this out, okay, to the data buffer, then the RDRF flag will be set. Okay, RDRF flag will be set, and then from there I will know that the data has been received. Okay, so once that flag is set, I can read from the UART register. Okay, now if I want to enable parity, okay, so this UART0 C1 register, we're not going to touch the rest of it, but only this last 2 bits again is only optional. Okay, you don't necessarily need to use it. Okay, for our project again, you don't really need to use it. Okay, because it's quite a simple 1 byte transfer only. All right, so you don't need to have it, but if you want, you can implement it. All right, so if you want to have parity enable in your data, then you can enable it. All right, so on the receiver side, you can use that to check whether the parity error has been flagged or not. Okay, so to enable the transmit and receive module, you go to the UART 0C2 register. Okay, so you have two bits here: transmit enable and receive enable. So these 2 bits will be able to either enable the transmitter or receiver or both. If I want interrupts, then I set the TIE and RIE. Okay, so transmit, interrupt enable, and receive interrupt enable. So these are the 4 bits that you want to either enable or disable depending on what you want to do. Okay, so for the status register, okay, the flags that you want to read are the transmit data register empty and receive data register full. Okay, so of course, if you are doing the polling approach, then you manually read them. If you're using interrupts, then the interrupt will automatically trigger, okay, when the event occurs. Okay, so we will look at that, okay, when we are examining the sample code. What I will do is, I think I will move over to the code. Okay, to see. Yeah, okay, so let me go over to the code directly. Okay, so we can see how it works over here. So these are the default settings. All right, so we are going to be using port E, pin 22 and pin 23. Okay, so what are these pins mapped to? Okay, so we can look back at our multiplexing over here. Okay, port E, pin 22 and pin 23. So you can see that it maps to UART2 transmit and UART2 receive. Okay, so these are the 2 pins that we will be using. Okay. So for the lab, we are going to be using, initially we're going to be using the transmit alone, just to observe the signal being generated. Okay. But in the actual project that you're going to implement, you don't need to transmit anything. Okay, because the transmit is actually coming from the app. Okay, your KL25Z is only going to be receiving data. Okay, so we're going to just explore the transmit just to observe the waveform. But for the project, you're actually only going to be receiving data. Okay, which I'll also demonstrate later. Okay, so we're going to be using these two pins. All right. So this is the interrupt priority. Okay, this one we will look at it later. Okay, so the first thing is you want to enable the clock. All right. So since we are using UART2 and we're using port E, I need to make sure that both the clock gating for both these modules is turned on. All right. So that's the first thing over here, enable clock gating. All right. So by now, I think you are already quite familiar with the sequence, correct? What we do step by step. Okay. The next thing is you want to enable the UART functionality for both port E22 and port E23. So looking back at the data sheet, okay, you can see that this port E22 and 23 is actually mapped to the alternate 4 function. Okay, alternate 4 function. So that is why over here I select the mux setting as 4. Okay, so that is to make sure that these two pins will now be mux to the UART transmitter and receiver. Okay, now this part, the clock setting. So now the default system clock. So in this code here, all right, I've already set the clock setup to 1. So the default system clock is 48 megahertz. All right. Now, the way the KL25Z is designed is such that this bus clock, that means the clock that is actually used by the UART module is half of the system clock. Okay, so if my system clock is set at 48 megahertz, okay, then my bus clock, okay, that means the clock that is used within the UART module is half of that. Okay, so this is again by default the way the module is, the hardware is designed within the controller. So we can't change this. Okay, so the bus clock is half of the system clock. So this is the first thing that you must note. So if my system clock is at 48 megahertz, then I divide it by 2. So the UART main clock is running at 24 megahertz. Okay, next is the divisor. So this divisor is what? This divisor is coming back to the earlier slide over here. This. Okay, so basically I need to come up with the value for the SBR register. Okay, so this SBR register value, if I rearrange this, what do I get? I get that the SBR value is bus clock divided by baud rate times 16. Okay, so if I rearrange this, okay, so this SBR will be equals to, okay, the UART clock divided by baud rate times 16. Okay, so that is basically what we are doing here. Okay, the UART clock, which is the bus clock, divided by baud rate times 16. Now, what is the baud rate? Okay, so the baud rate, okay, is set to okay, so the baud rate is the parameter I passed in when I call this function init UART2. Okay, and the baud rate is this, okay, which is defined as 9600. Okay, again, this is just a baud rate that is going to communicate between the KL25Z and the ESP32. Okay, so if you want to choose other baud rate, it's fine. Okay, because as long as whatever baud rate you choose here matches the baud rate from the ESP32, that is fine. Okay, in our case, in my demo, I'm using 9600. That's why I set this. Okay, so now the last part is the you get the value already, the value to set for the divider. So this divider is what? Okay, is to do this. Okay, because this is your main clock, your UART module clock, which is at 24 megahertz. Okay, and now I need to divide this by number to get the transmit baud rate and the receive baud rate. Okay, so what I need to do is I need to make sure that the value that I get over here is generated, calculated using this formula here. Okay, so when I calculate this, I get a value, but this is a 13-bit value, correct? SBR 12 to 0. So it actually is broken up into two registers. Okay, it's broken up into two registers, which is the baud BDH and BDL. Okay, so let me show you that over here. Okay, so this is the BDH and BDL. So there are the full 13 bits is broken up into two registers. So the UART BDL baud register low is the lower 8 bits, and then the upper 5 bits over here. We get upper 5 bits. Okay, so in order for me to take the value and put it correctly, what I need to do is I need to take the call this macro, okay, to break it up into two different registers. Okay, so this is a macro definition, so you can look inside the definition file where you will take the data and shift it, okay, to the correct bit position. All right, so in the baud rate low, it is the actual value itself, and for the baud rate high is basically the value shifted right by 8. Okay, but this one will do a masking for us. All right, so you can see that you will do a mask, okay, to make sure that it only takes the upper 5 bits. Okay, the upper 5 bits over here. Okay, so that is done again through the macro. Okay, so these two lines is to make sure that whatever value I get is updated to the baud rate high and baud rate low registers correctly. Okay, so that is what this is for. Okay, to set the correct baud rate, this entire section here. Now, the next thing is setting the C1, S2, and C3. Okay, so if I look at these registers, how come I set everything as 0 over here? Okay. So let's look at it. So C1. Okay. So the C1 register, again, all of this we don't need to worry. Only thing is the parity. In our case, like I said, I'm not using parity, so I'm not going to configure this. Okay, so C1, what was the other one? C1, S2, and C3. S2 is this one. Okay, so the S2 is again a lot of the error related flags. Okay, so we are not going to deal with any of, doing any of this sort of error checking over here. All right, so I'm not going to do that. Okay, so I set it to 0. And the last one is the C3 register. Okay, so in the C3 register, okay, again, all of this is to enable some of these interrupts, okay, for error checking. All right, and this R8 and T8 is only if you are transmitting 9 bits at a time. Okay, so the 9th bit of data. In our case, we are only dealing with 8-bit data, so again, that is 0. Okay, so we can set all of this to 0. That means there's no parity, and we are dealing with 8-bit transmission. Okay, and the last part here is to enable transmit and receive. Okay, so to enable transmit and receive, we go to the Okay, you go to the UART C2 register. Okay, so let me show you over here. Yeah, so under UART C2 register, basically there is two things. Okay, the one is the transmit and receive enable, the other is transmit interrupt and receive interrupt. Okay, so in this example here, I'm not using interrupts, I'm using polling. So I just enable the transmit and I enable the receive. Okay, so the receiver is on and the transmitter is also on. Okay, so that is what is happening here. All right, so in my code over here, what I'm doing is I just call the UART2 transmit pole with a fixed value. Okay, 0x69. Okay, and what do I do in the UART2 transmit pole? Okay, so let's look at the code over here. So what I do is I keep checking for the transmit data register empty. Okay, that is in the UART2S1 register. Okay, so let's look at this register again and see that correctly. UART2S1 register. Okay, so we are polling for this transmit data register empty flag. So what does it say here? All right. So TDRE is set out of reset, and when a transmit data value transfers from the transmit data buffer to the transmit shifter, leaving room for a new character in the buffer. Okay, to clear the TDRE, read UART-S1 with TDRE set and then write to the UART data register. Okay, that means I must wait until this flag becomes 1. Correct? Because when this flag becomes 1, then I can say that the data register is empty. Okay, so that is basically what I'm doing here. I am keep checking, okay, for this, okay, to make sure that the, so initially when I write to the transmit data register, okay, it will be 0, correct, because it is not transmitted yet. Okay, so it's still in the process of transmitting. So while I'm still in the process of transmitting, this, okay, will be, this is a not, correct, so this not will make this a 1. Okay, because this register end with 0, then it will become a 1. Then eventually when it becomes 1, that means the transmit data register is empty, is true. Okay, then this check will become false. Okay, this check will become false, and then what am I able to do? I'm able to take new data and update the D register. All right, so if you look back at the block diagram, okay, basically what we are doing here is, okay, we want to wait until the transmit data register here is empty. Okay, because once it is empty, then I can write new data to it. Okay, so how do I know it's empty? By looking at the TDRE bit. Okay, by looking at TDRE bit, I know it is empty, so I can write new data to it, and that new data can get shifted up. Okay, so that is basically what, okay, that line is doing. Okay, so once I write to the D register, then the process of transmitting it out serially just happens automatically in the background. Okay, it just happens automatically in the background, and you start to see the data coming out on the serial port. Okay, so that is basically what you have over here. All right, so let me show you this. All right, in action, so you have an idea what is happening. Okay, so give me a minute here. Okay, so this is basically what we have. Okay, so in terms of the hardware, okay, to check the transmit, basically you need to connect to the transmit line. Okay, and the transmit line is here, pin 22. Okay, pin 22. Where is pin 22? You can look back at your pinout over here. So that is the top right hand corner, okay, on the left hand side, the 4th pin. Okay, which is basically what I have here. Okay, let me bring it closer. That is your pin 22. okay, the transmit pin. All right, so when I run this code, okay, when I run this code, basically what is going to happen is it's going to continuously transmit data on that line, and the data that I'm going to transmit is in this case is the fixed data, which is 0x69. Okay, so let me run this. Okay, so let me adjust the thing to show you the scope. Okay, so you can see the data there. All right, so how do I interpret this data? Okay, so let me draw it out over here. Okay, and then we can interpret the data. So what you are seeing is this. Okay, so this is basically the waveform you're seeing. Now, so this is basically the idle line. All right, by default, the idle line is high. All right, and the indication of data being transmitted is when the line gets pulled. So this is your start bit. Okay, this is a start bit, and if you look at the data that follows from there, what do you have? So you have 1, 0, 0, 1, 0, 1, 1, 0, and then this is your stop bit. Okay, when you go high. Okay, so this is actually what? So if you look at it in terms of by hexadecimal, this is your 9, and this is your 6. Okay, so I'm transmitting 0x69. Okay, but over here I'm getting it as 0x96, or what I'm seeing is 0x96. Okay, so why is that so? Okay, this is what I'm transmitting out, that means coming out of the pin. All right, and what I'm observing on the scope is 96. Okay, and the reason for that is, okay, if you observe just now, some of you may already have seen the reason why. Okay, because over here, okay, you can see that the least significant bit is the one that gets shifted out first. Okay, followed by the most significant bit. Okay, so you start off from the least significant bit, and then you go to the most significant bit. Okay, so that is the reason why when you look at it from the waveform, okay, you're actually seeing the in the reverse order. Okay, and this is actually quite important, all right, to note whether the transmit module is transmitting in the most significant bit first or least significant bit first. All right, because when you expect to receive data, you also need to know when the data gets shifted in which direction it will get shifted in. All right, so all of this sort of plays a part to make sure that sometimes the data is correct, but you thought it was in one direction, but actually it was in the other direction. All right, and then things don't work. Okay, so that is why, you know, using a scope and things like that to check what is really happening can sort of clear things up a bit. Okay, so that is basically what you're going to be doing for the lab. Okay, you're going to be doing for the lab just to make sure the transmit module is working. All right, and after that, of course, you can go on to explore the interrupt sort of version of it as well. Okay, so what I'm going to do now is we're going to take a break. Okay, when we come back from the break, I'm going to go through the lab manual for this week, the additional ones. All right, so what I would like you to do is to go to Luminous. Okay, if you have not downloaded the latest lab manuals, all right, please go and download it. Okay, so there's 3 lab manuals actually for this week. Okay, so one is your main lab 5 lab manual, all right, which is there, and then there is 3 additional ones. One is for getting started with ESP32, then ESP32 web server, and finally the app control with the ESP32. Okay, so I'm going to be sort of demonstrating this part over here and sort of giving you an idea how this whole thing comes together. Okay, so that you know how to put everything together, all right, when you are working on your app. okay, and your whole system. Okay, so I'm going to talk about this in more detail after we come back from the break. Okay, so now it's 11, so we will take a 10 minutes break. Okay, we'll come back at 11:10. Okay, and then I will talk about this aspect in more detail. Okay, so I'll see you all back here in 10 minutes time. Okay, so welcome back. All right, so let's carry on with the review of the material. Okay, so if you look in your Luminous, okay, there are 3 documents. Okay, so let me just briefly go through the 3 documents. So so this week we will also issue you the ESP32. All right, so each group will get one. All right, so some of you may already have been issued when you first drew out the project kit. All right, so if you have been issued with it, then just let us know. Okay, then the rest of you will be getting one. Okay, so this ESP32 is quite a powerful board. All right, it's a lot of features built in, and I mean, I have plans to use it to do a bit more stuff as well. All right, in future batches. All right, I just haven't sort of gotten down to finalizing it yet. All right, so in this first handout, okay, I'm going to I guide you through the steps of how to set up the board correctly, okay, and run some example code, which is the Wi-Fi scan. All right, so this Wi-Fi scan code that you run, okay, basically will be able to switch on the Wi-Fi module. All right, and using the serial monitor, you should be able to detect the Wi-Fi networks in the area. Okay, so as long as you're able to see something like this, okay, based on the Wi-Fi networks that you can detect, then your ESP32 is fine. All right, so one of the common issues that some students have faced is the cable. Okay, sometimes I don't know why nowadays cables are not so reliable. All right, the USB cable itself may have some issues, and because of that, you don't seem to be able to download the code or get the serial printout correctly or things like that. Okay, so so before you see if it's a board issue, try to maybe change the cable. Okay, or if you have your own USB cable, the micro USB, all right, also you can bring that along. Okay, then you can use that, okay, and see whether it works. All right, so the ESP32 again has a built-in Wi-Fi module which will automatically be able to scan and connect to the network. All right, so far again the easiest way of running this is to use one of your phone hotspot. Okay, again the traffic is very little. It consumes very little data. Okay, so it's not going to really have any impact. So you can just switch on your mobile hotspot, okay, and use it when you want to do the testing for the robot. Okay, so that is the first thing, okay, to make sure your ESP32 is working correctly. Once that is done, okay, you can go on to the next part. So in the next part, basically what we are doing is we are going to take note of the Wi-Fi of the we're going to set the SSID and password. Okay, so this is through the ESP32 web server AI2.c. So these files I will upload in a while, okay, to the Luminous. Okay, so from the file, all you need to do is change the SSID and password to whatever hotspot that you are connecting to. All right, and it should be able to show you the IP address. Okay, now this second part over here, which is static IP. All right, okay, so one of the things that students said that this doesn't always seems to be static, in a sense that, okay, if today you use your hotspot and then next week when you switch on the hotspot again, you will get a different IP address. All right, and then you realize that you may need to keep changing your code in the in the ESP32, okay, every time you switch on the hotspot on a different day. Okay, so one of the ways to go about this is instead of doing this step 2, that means instead of creating a static IP, you can let the IP be dynamic. All right, that means you just take the IP address that it connects to. Okay, because it's still going to connect to the same hotspot because the SSID and password are there. Okay, but once it's connected, it will give you the IP address. Okay, and instead of doing this IP address being static, okay, you can actually sort of configure that in your code. Okay, which your app development code, which I will show you later. Okay, so this static IP is optional. If you think you don't want to do it, you can skip this part over here. Okay, now the third part is once it's connected, all right, you can actually see how it works by very simply opening up any browser, okay, and keying in the IP address. Okay, this web interface control works when the web browser that you're using is on the same network as your ESP32. Okay, all right, so once you are able to open up and you see it's connected, you just open up any browser and you key in the IP address, you should be able to see this. Okay, so over here what I've done is I've just created a simple hardware circuit, okay, to connect the LED. All right, so the LED connections, let's see, where is it mentioned? Okay, so this is just to connect to one of the pins. All right, so the pin is actually given in your code, in the code there. All right, again, you don't necessarily have to do this on the red LED, as long as you see that you are able to get the status. All right, that means you know that you are actually connected. Okay, so this code over here is already inside the this ESP32 web server AI2.c. All right, so where is this? Let me show it to you over here. So over here, all right, so this is the ESP32 code. All right, so when you are sending any command, okay, the command to send to the ESP32 is actually very straightforward. It is just the IP address slash with a string, okay, the string with which you want to send something, all right, or send a command. So in this case, status is one of the command, all right, which I am sending. So over here, when you see that I have the status being sent in my web browser, okay, I'll get this response. Okay, this response is basically based on the code over here, which tells me that I will print out Wi-Fi connected plus my IP address. Okay, so the on rate and off rate, that is basically I connected an LED to digital pin 26. So this digital pin 26 is on the ESP32 itself. Okay, so on the ESP32, okay, so if you see down here, pin 26, okay, pin 26 I connected an LED to ground. Okay, so the idea is whenever I send a command, okay, whenever I send a command through my browser or through the app, okay, I will always on or off the red LED on the ESP32. Okay, and why do I want to do this? Why do I want to do this? Because there are two places where things can go wrong. Okay, there are two places where things can go wrong, because in your design, okay, basically what you have is you have two parts to it. One is your app, okay, or your browser, okay, sending some data packet over to ESP32. Okay, so that is the first layer. Now in the second layer, ESP32 is taking that data, interpreting it, and sending it over to the KL25Z. Okay, and this is using the Wi-Fi, and this is using the serial. Okay, so now when I send a command over, so let's say I send a command over to say forward, okay, and your KL25Z is supposed to respond, right? Supposed to respond and make the motor move or something, and it doesn't. So you do not know where the failure happened. Correct? You do not know where the failure happened. So by making sure that whenever a command goes to the ESP32, the ESP32 has received that command, okay, I actually will on the red LED. Okay, so this is just to give me an indication that, okay, the ESP32 actually received the command. Okay, so the part where something could have gone wrong is maybe over here. Okay, or the KL25Z in the code itself, it never checked something properly. Okay, so there are two layers of communication. First, the Wi-Fi from the app to the ESP32, and from the ESP32 over to the KL25Z. All right, so coming back here, so you can see that whenever I send a command over, I always output high or output low. Okay, for example, on red, off red. Okay, then on green, off green, and so on. Okay, so of course I can put different color LEDs on different pins to differentiate various commands, but I just sort of simplified it as a single LED for any command. All right, just to see that it was working. Okay, so that is the code over here. Now, let's look at the next part of the communication. So the next part of the document over here first is these commands right now. Okay, this on red, off red, all of this. Currently, you can send it through a browser. Okay, and for the browser, I strongly recommend using Opera or Firefox. Okay, Chrome has always been a bit of an issue. Okay, sometimes it works, sometimes it gives some funny error and things like that. Okay, so again, from what students have tested, also they found that using Opera browser or Firefox seems to be quite reliable and consistent. Okay, Chrome, again, it might work, it might have some issues and so on. Okay, so once you test it with the browser, okay, once you test it with the browser, and you can see that I'm getting a response over here. Okay, so as long as you see the response coming here, means that the code is correct, the code is working. But if you don't see, because the response here is based on the text. Okay, now if you don't see the LED light up and so on, that could be a hardware issue. Okay, but as long as you see that the response is coming on your browser, okay, whenever you key in IP address with a slash on red or off red or things like that, that means the Wi-Fi connectivity is correct, is there. Okay, now the next part is how can I sort of put all of this inside the user interface. So that is where the app interface comes in. All right, so I hope you have explored the app inventor that I talked about last week. Okay, so over here I give you the step-by-step instructions on how to integrate that inside the app. Okay, so the basic user interface design, I think you can either go to my website, okay, over here to learn the basic concepts, or to the app inventor website also. Okay, and then from there you just need to call the web functionality to specify the URL, okay, and then get the response. Okay, and that response will be able to be printed out, okay, when the ESP32 replies back. Okay, so that is the basic user interface design that you can try out, okay, just to make sure that the red LED is on and off. Going on and off. So this second document is to just check and make sure that this part of your system is working. Okay, do not proceed unless this is working. Okay, because if this is not working, then the next part is definitely not going to work. Okay, so you need to make sure that this first part, that means using an app, okay, you are able to send data over. Okay, as I mentioned before, you do not need to use App Inventor. You can use any other tool, software that you like. As long as you are happy with the user interface, you can control the robot, you can send all these commands to the IP address, that is fine. Okay, so this app Inventor is of course one of the easy ways of doing it. If you want to try something else, it's also fine. Okay, so once you're done with this, we are confident that this first half of the system is up and running. Okay, now the last part is the serial interface to the KL25Z. Okay, so for that serial interface to the KL25Z, we need to open up the third document, which is this. Okay, so the app to control the ESP32 web server with the KL25Z. Okay, so for the KL25Z, all right, the interface design is basically going to be this. All right, so for the ESP32, we are going to be using one of the serial ports, which is serial 2. Okay, and we're going to connect it to the receive of the KL25, which is port E pin 23. All right, so over here, basically what is happening is over here, what I have is I'm transmitting, and here I'm receiving. Okay, so the ESP32 is transmitting the data, KL25Z is receiving the data, and this is through the serial interface. Okay, this is through the serial interface, which is over here, and the baud rate is at 9600 bps. Okay, so where is this code in the ESP32? So in the ESP32, I already start the serial over here, then serial 2. The serial 1 is the one that we use, or the default serial port is the one that we use to send and download the code to the board. Okay, the serial 2 is the one that we are using to send data over to the KL25Z. Okay, so you can see that over here in the code, all right. So all this file I'll upload to Luminous, so you can use this as a baseline code to do your programming. Okay, so this code over here, you can see that every time I send a command, whether it's status, on rate, whatever, I do a digital write. So this digital write is just the red LED that is on the board, the ESP32, connected to the ESP32. But at the same time, I do a serial transmission. Okay, I do a serial transmission on the serial 2. Okay, and this data is the one that is being sent over to the KL25Z. Okay, why is sent over to the KL25Z? Because of the hardware design over here. Okay, so whenever I say serial 2.write is coming out on the TX2 pin, and I'm receiving it over at the port E23. Okay, the same UART2 module that we just saw. All right, so that is what is happening over here. So I'm doing a serial 2.write with specific bit patterns. Okay, now let's look at the KL25Z code. So the KL25Z code is actually very similar to what we saw just now. Okay, except that, okay, instead of transmitting, I'm doing a receive. Okay, so the configuration is all the same because I'm still using 9600 bps and so on. So the rest of the code is the same. But only thing is, instead of transmitting, I'm doing a receive. Okay, so I will receive the data. So what is the data I will receive? Okay, so I will receive a packet of data. Okay, so in this case, I've given you some example code over here, or example data packet. Okay, this is just example only. You don't need to follow. Okay, so I just set aside, okay, 30 is off red LED, 31 is on red LED, okay, and so on. Okay, and over at my code over here, what do? Once I receive the data, I will decode it, and I will on or off specific LEDs. Okay, depending on whether the data is for red LED or green LED or blue LED. Okay, so that part, the decoding of the data and activating an LED or a motor or the audio is all up to you to decide. Okay, how you want to look at the bits and do the decoding. All right, but the whole idea is, what is happening is whenever I send a data over, all right, okay, I also in that same check, I also send a serial data across to the KL25Z. Okay, and that serial data will be interpreted to perform the appropriate action. Okay, so let me show you the whole thing, all right, how it all comes together. Okay, so here what you have is, you have the app, all right, All right, and you have the red LED. You have 3 buttons over here. All right, and you have a check Wi-Fi status button. Okay, so before this, maybe I will show you the app over here. All right, so in the app inventor, you can create all of this. All right, and this is exactly what I've given you in the example as well. Okay, so nothing new here. Okay, you just call for each button, you call the web URL with your IP address. Okay, and the specific function that you want with the slash. Okay, so okay. Okay, so let me come back to this first. Okay, so here you can see that the app is already compiled. So this is the compiled APK file. So I'm no longer depending on the web link, okay, to update the code. So this is already a finalized code. So when I click on the check Wi-Fi status, okay, it will show me Wi-Fi connected and show me the IP address. All right. So right now what I have is I have, okay, so you can see down here I have my ESP32 connected to the KL25Z. All right. Again, this connection is exactly the same connection as I showed you here. Okay, this connection. So it's only one wire transmit to receive and another wire to ground. That's all, nothing else. Okay. Now, so what is happening is now the ESP32 and the Android app over here, they are both connected, okay, to the same Wi-Fi, okay, which is my hotspot. Okay, so right now if I say red LED on, red on, okay, you will see that, okay, 2 things happen. Okay, one is the red LED on the ESP32 over here gets lighted up, okay, which is the one over here. Okay, then at the same time, okay, at the same time, the red LED on the KL25Z also gets lighted up. All right. Now, if I say red off, okay, you can see that the LED over here also is off. Okay, the LED over here is also off. Similarly, when I press green on, okay, the green on the KL25Z lights up, green off, the green goes off. Similarly, blue on, the blue off, and the blue goes off. Okay, so whichever button that is on, I will still on the red LED on the KL25Z. Okay, again, that is just for me a simple way to just make sure that the ESP32 has received the data. Okay, but the KL25Z is responding based on whatever information is being sent over serially. Okay, now let me just show you the waveform, all right, just so that you can see the relationship. Okay, so I'm going to capture the signal for the red LED on. Okay, just so that you can see what is happening. Okay, so I'm going to press the red LED on button here. Okay, so the signal is captured over here. All right, so the red LED on, this is the red LED on over here. Now, how do I interpret this? Okay, so again, let me bring up my OneNote here. Okay, so if I were to draw out the waveform, again, this is what I get. Okay, so this is your start bit. Okay, so 1 0 0 0 1 1 0 0, and this is your stop bit. Okay, so what is this data? So this data is actually 0, x, 1, and 3. Correct, because this is again 0001, and this is 0011. Okay, so this is 1 3. Okay, but the data being transmitted out, okay, for red LED on, okay, if you look at your code over here, is 0x31. Okay, so again, why we are looking at it is the reverse order is because the LSB is shifted out first. Okay, the LSB is shifted out first. So I'm writing 31, okay, but on the scope, I'm looking at it in the reverse order. Okay, so it is 1 and then followed by the 3. Okay, so that is what you observe over here. Okay, and that's how you interpret. Now, over at the KL25Z, what is happening? Okay, so this data is going into the KL25Z, right? So this is the data going into the KL25Z. Okay, receive pin. Okay, it's going into the KL25Z receive pin. Now let's look at the KL25Z receiver block. Okay, so if you look at the KL25Z receiver block, what is happening? The data that is coming in over here gets shifted in all the way. So the first data that comes in goes all the way here, all right, to the end. Okay, and followed by the last data. All right, the last data here. All right, so this is your LSB and this is your MSB. All right, so even though I transmit as LSB first, but when I get shifted into the register, okay, it will also be LSB first. All right, which means that when this data goes in all the way, this will map to the LSB and this will map to the MSB. So the answer that I will get in my receive data, okay, in the UART register will be 00110001, which is 0x31. So it still works out nicely. Okay, so even though it's going out in the reverse order, I also expect to receive it LSB first. So the data that I interpret is still the same order as what I actually transmitted out. Okay, so in my code, okay, in my where's my mouse? Okay, so in my KL25Z code over here, okay, when I receive the data, this RX data, okay, you can see that the data, okay, maybe I'll put a breakpoint here. Okay, so let me do it one more time to show you. So if I press red on one more time, so let me show you. I'm going to press the red on one more time. Okay, so I have here, and you can see that the received data, RX data is 0x31. Okay, I'm not sure if I can zoom in here. I can't zoom in on this window. Okay, but the RX data, if you see down here, is actually 0x31. Okay, so it matches the theory that we just covered. All right, that means even though I transmit LSB first, the receiver is also going to shift it all the way to the LSB. Okay, so the order still comes back to the original order in which we thought about the data. Okay, and this 3.1 comes from where? This 3.1 comes because of the way I designed this particular protocol to say that on red LED is 0x31. Okay, so basically this sort of puts everything together. Okay, so this is basically what you need to work on, all right, this week and next week, okay, to make sure that you have the entire system up and running. Okay, that means you are able to use your app, okay, use your app over here that you create, okay, to send some commands that will go to the ESP32, and from the ESP32 go to the KL25Z, and the KL25Z. Okay, if you can control the LED, that's more than enough already, because then you can just replicate that to control anything else. Okay, so controlling the LED is the first step. Okay, subsequently you can do everything else. Okay, so I hope that it is a bit clear now, correct, how you're supposed to put everything together and how everything comes together as one. Okay. Again, this protocol, the app, all of these are just examples only. Okay, you are free to design it whichever way you like. Okay, as long as the idea of being able to transmit from the app or user interface right down to the KL2YZ is achieved, then I think that is fine. Okay, so again, this demo is you only need to do it after you come back from the recess week. Okay, so you have this week plus next week plus the week when we start again. All right, to do a demo of this functionality. All right, so you don't need to hook up any motor or anything like that. As long as you can demonstrate that you already have some user interface, okay, to control the RGB LED, that is enough. Okay, so again, it is something that is doable as long as you plan it out and you divide the work within your team. Okay, that I think should be something that you can achieve. Okay, so that sort of wraps up today's class. Okay, so so just start to work on it and build it up slowly. All right, when we come back after the recess week, okay, we will go full swing into the OS part. All right, and then how we can look at how we can integrate the OS architecture towards the project. Okay, so this getting all these low level hardware device drivers ready, the app interface ready, and this connectivity up and running sort of gives you that confidence, and it actually is allows you to sort of manage your project better, because some members of the team can start to build up the hardware aspects while the rest of you can focus on the software development and the OS integration as the weeks go by. Okay, so again, you need to sort of discuss within your team how you want to spread out the work, okay, and then use the remaining few weeks very carefully. Okay, so that's all I have. If you have any questions, you can stay back and ask me. If not, I will see you this Friday in the lab.